All right. So I'm going to pull up the notes from Wednesday. Okay. I'll pull them up here as well. All right. So we were talking about this whole idea about the radon concentration, right? Okay. So I believe we're getting to the point where we need to start thinking about what the graph looks like. Did we do the graph yet? No. Okay. So you guys need to work on the graph for me here now. Okay. So be graphing that in that graphing that one. I need you to follow what Brandon did for me. Okay, Wyatt. Thank you. And get some ordered pairs on your graph for me, and then we're going to start analyzing this a little bit and seeing how this graph is different from when we did the house graph on Wednesday. Okay. So if I recall from the table, now here's the deal: you're going to want to plot these columns. Okay. You're going to want to plot the half-life column, and then you're going to want to plot the concentration column as ordered pairs. Okay. And the half-life column is your X column, and this one is your Y column. Does that make sense? So here and there, and it's how you can generate your ordered pairs. Okay. So go ahead and get those down. So you're going to start at 0, 400 right here. Then you're going to do 1, 200, which is right there. And then it's 8, or sorry, it's 2, 100. My mistake. So there, and then how many do we have? 3. Okay, so one more. And it's 50, right? That look about it? How's that look, everybody? Okay, good. Excellent. Excellent, excellent, excellent. All right, so those are your ordered pairs. Now we're going to do a couple of predictions too now. All right, and you can do these with your group mates, so everybody has a collaboration time. Can I move on from the graph? You guys got your graph okay? Okay, good. All right, so again, is this a linear graph? Is this a linear relationship? Absolutely not. Okay, rate of change is not constant. Right, okay. Rate of change is not constant. Very good. All right, so number 7 answered. Okay. So, guys, work on number 8 for just a second. Okay, Renee needs to know the concentration of radon in the house after 20 days. Okay, so on your fingers, show me how many half-lives are in 20 days. Okay, half-lives of radon, because other elements have different half-lives. Okay, so how many half-lives of radon are 20 days? One half-life is 4 days. 20 days is how many half-lives? 5. Everybody okay with that? Good. Use that number and tell me how much concentration of radon should be in the house after 20 days. Okay? Put that chart up there, that graph up there again for you so you can take a look at it. Okay? Sorry. All right, everybody got an answer for me on this one? You can continue the table pattern, you can continue with the graph pattern. You really didn't have to do any kind of equation solving or anything like this on this one. Turn and talk to your roommates for 30 seconds to get the same answer for 5 half-lives. Okay? Go. All right. I'm going to roll. Okay? I'm going to roll. All right. I got a number. And Caitlin's sitting in that seat. Actually, I take that back. Emily's sitting in that seat. Okay. Okay, 12.5. How'd you get your answer?
Well, I knew it before because I'm sitting there being like, oh, after 4 it's 25 and after 5 it's 12.5. But if you do it in the equation, f of x equals 4 metric times 1/2 raised to the 5th.
Yep, good. Okay, are we okay with 12.5? Good. Now, how many half-lives would be in 22 days? Okay, 20 days is 5 half-lives. So 22 days is how many half-lives? Raise your hand. Help me out with that one real fast. Tony? 5.5. Yeah. Okay. So predict real quickly how many you think is going to be in 5.5 half-lives. Okay. All right, you guys have a prediction for me? Just predicting at this point. Just write down a prediction, okay? We'll come back and probably visit that again in just a few minutes, see if you guys are on the same page. All right? Now, on Wednesday, when we did the house problem, the value of the house went up, right? Okay? Today, the concentration radon is going down. So, on Wednesday, our example was based on exponential growth. Okay? The value of the house grew exponentially over time. Today, though, the amount of radon is going down exponentially. That's an example of exponential what? Decrease, or we sometimes call it decay. Okay? Decay means it's going down. All right? What's the constant factor for our situation? What's the constant ratio? Okay? Each half-life, the amount of radon is decreasing by what amount? How much is left every time, Eliza? Half. Are we okay with that? Yeah. So that's number 10. Now, what I want you guys to do is write an exponential function for this. Okay? Is 1/2 the A value or the B value? Remember the formula here? Okay? The format is A times B to the x power. Okay? Now, f of x, r of t, h of t, you can change the variables that you use. That's fine. But the formatting is still going to be the same. Okay? So you have to figure out your A value and your B value here. So do that and then write your function. Okay? Everybody good with that? Okay. Work on that for a minute, and then you're going to work. How about if you just do that with your groups real quick? Get your function ready to go. Okay? I want to try to get some other fun stuff here today with you guys. You guys have your function ready to share? Talk to your group mates for 30 seconds, and then we're going to roll the dice again. Go. Well, you're close, actually. Oh, that's not the right problem. You need A and you need B. You know what A and B are? Okay. Go back to the previous section. Notes. Oh, right there where you highlighted. It has it all written out for you. A is
for exponential growth.
it's the same format. No, this is just we're just writing an exponential function. The situation's exponential growth. Does that make sense? Okay, so it was a growth example, but the exponential function is going to have the same formatting as that on your thing. Mm-hmm. Yeah. Okay. It's that the situation modeled a growth. Okay, it's not that function specifically for growth. Okay, because B can be anything, any kind of factor, ratio. All right, how are we doing up here, guys? Everybody good? Everybody okay over here? Yellow group, you guys ready to go? All right, I'm rolling the dice. Here we go. Let's see what you guys come up with. All right, Blake. Some things never change. Okay. All right. What's your initial value? How much radon was in the house when we first started this experiment? 400. What's the constant ratio, Blake? What's the equation? What's the function? We'll do it as R of t. So R of t equals what? To the well, that's just for finding it for 5.5 half-lives. Just t is any amount of half-lives, right? So we just need to have a t there, and we got it. Okay, nice job. Everybody okay with that? Good. All right. So just real fast, R of t is the amount of what? Don't everybody tell me at once. What is it? Raise your hand. Amount of Ray. Oh, yes. Okay. All right. Is this because it's Friday and you guys are ready to have a weekend? I understand that sentiment. Okay. T is the number of half-lives. Yep. Okay. Work 13 and 14. And use your calculators. What I did was I just copied down what we already established on problems 8 and 9, okay? Take 1 minute on your calculator, get those values. How are we doing, kiddos? Okay? What will it in? What's up here? Did you do 1/2 to the fifth already in the calculator? Remember 1/2 is 0.5, right? So in your calculator, you're going to be spread by the result. 0.5 to the 2, 0.5 to the fifth power.
Oh.
You're welcome. Okay. Oh. give you 0.5 to the 20th power. You're not going to do that like that. Would you like a shortcut?
Yeah.
0.5. No. 5. It's 5. 5. Done.
Thank you.
Who's got your back? Okay. All right, check with your roommates, guys. Yes. Both.
My calculator will pretty sure I have it. I'm not sure if I do.
I didn't get the rest of it.
All right, with me, guys, real quick. I'm going to do this real quick on the Desmos calculator, okay? So I have 400 times 1/2, and I'm going to raise that to the 5th power, right? Because that's 5 half-lives. Final answer is 12.5. Is that what we were supposed to get? Remember, 0.5 is the same as 1/2. That's our constant ratio. Okay. Pardon me? 0.5 is the same as 1/2 as a decimal.
Wait, which one are we supposed to be doing?
Number 13. And then number 14. Okay. So we're taking our function. I just changed 1/2 to a decimal. I just made it 0.5. That's the only thing. Okay. So I have 400 times 0.5. We have 5 half-lives. That's to the 5th power. And the final answer is 12.5. Okay. Which was our prediction, right? Wasn't that our prediction? Okay. All right. Alex, question? Did you do it? Oh, did you do it? Did you do it by days instead of by half-lives? Remember, T is the number of half-lives. There's 5 half-lives in 20 days because the half-life of radian is 4 days. A radon. Okay. So does that make sense now? Okay. Yeah. There's 5 half-lives in 20 days for radon. Okay. Each one's 4 days. So you have to split up that amount of days into equal half-lives. Okay. So what's it gonna be then for 5.5 half-lives? We'll just add a decimal point. You get 8.83, right? Or 8.84. So this one right here was 12.5, and then this one right here. Okay, 1/2 to the T. It would be, I can't write it in that small space. 8.84. Okay, Alex? Shouldn't. Okay. No, you're gonna have decimal answers on your assessment. Okay, no, they're not gonna be all nice numbers. Okay, you guys are gonna have to expect some decimal numbers on these. Now, I can't guarantee anything on this. Okay, but it's not about the numbers you get; it's about the process you do to get them. All right, so if you do the correct process, you're gonna get the right numbers. Does that make sense? Okay. Okay, so I like number 15 real quick. Let's just discuss this for a second. Will the concentration of radon in the house ever be 0? Okay. What do you think? Turn and talk. 1 minute. Go.
I mean, since it's going down, it has to end at some point. I guess that is true. It's not subtractive. It's always such a mystical. We're always gonna have some number.
So we could divide by 8. You can only do
It just destroys your calculator.
So, will it ever hit 0?
No.
No. Why not? You can help me out with that explanation. Mason?
Nothing divided by 2.
Okay, that's simplistic, but it works, right? Because you, regardless of what number you divide by 2, you're never going to get the equal 0, right? It's going to get smaller and smaller and smaller and smaller and smaller and smaller and smaller, and it's going to get really close to 0, right? But it's never going to be exactly 0. Never. Okay? But the ideal thing is to get that radon amount to an amount that is livable. And if you've had that issue before, then that's why you can never be actually equal to 0 exactly. Okay? Those are going to be maybe a little tiny trace of it. Very insignificant. Okay? All right. Number 16 is an important problem. Okay? And I'm going to actually add to it a little bit because we also need to talk about the constant ratio a little bit here in regards to getting these functions set up properly also. So this is going to be important. You might want to mark this one with a star in your notes. So this is important. Okay? The growth and decay ratios that we use for these two problems are simple in the fact that we can use those easily to get what we need. However, what if I said instead of this radon value decaying by 1/2 every half-life, what if it decayed by 30%? How would that change your function? Okay. So what do you think the function would be if I said 30% decay every half-life instead of a half? So instead of the amount reducing by a half every time, we reduce by 30% every time. How would that work? What would your function be? This is where you get to experiment and try some things out with your grouping.
With the same problem?
Yep, I'll put it up there for right now. Okay, we're going to do the same thing with the growth one too, so I'm going to put them both up here for a second, okay? Above number 16. All right? Okay, what would go and replace? What would we replace 1/2 with? Okay, for the decay function, if the value decreases by 30% each half-life instead of by a half. Mason, what do you think?
Would it be
0.3? 0.3. Does that work? Okay. Remember, this function is supposed to show you how much is remaining after that amount is removed. Okay. Let's think about this for a second. Let's just start with like $100, okay? If I have $100 and I'm going to lose 30% of it, okay? Do I have $30 remaining or do I have $70 remaining? 70. So what would it be? What would be the value B then in that case? 0.7. Okay? Because 30% is going to be removed, 70% remains. Does that make sense? Okay. Now, likewise, okay? Go back to the growth one for a second. All right. Let's say instead of the house value doubling every 10 years, it only increases 35% every 10 years. Okay. So my value for B would not be 2 anymore, it'd be something else. What would it be? 35%. Okay. Now again, think about this. You want the value to be larger, right? The next time, right? If you multiply by 0.65, well, your new value be larger or smaller than the previous value. Okay. Well, why is that?
Isn't it 1.35?
Well, you're very close with that. Okay. It is actually 1.35. I was thinking differently for a minute. Yeah, you're right. Okay. In each case, we have to start with a base of 1. Okay. So for growth, you add your rate. Okay. So, in essence, what happened was with the growth problem was the house value doubled, right? So every 10 years, it increased by 100%. 1 plus 1 is 2. That's how you get your constant ratio of 2. Okay? So for the radon example, it went down by a half each time. A half is 50%, right? So 1 minus 50% is 50% remaining. Does that make sense? So sometimes here, what we have to be able to do, if you're given a percentage amount, is you have to kind of restructure your function just a little bit, okay? So that it makes sense for you to get the values you're looking for, okay? So what did we do? For growth, we added the rate to 1. So if the rate was 35%, 1 plus 0.35 was 1.35, right? For decay, we subtracted the rate, okay? It was 1 minus 0.3 equals 0.7. That's how it became. You see how that works? I'm going to write up here underneath number 16 for you, okay? We'll do the actual problem here in a second, but I need you guys to realize this because these numbers here, 2 and 1/2, only really work, okay, if the rate's 50% or if the rate's doubling, okay? So we have to rethink things a little bit if that's not necessarily the case. And this is the way you can always get the rate correct, okay, the constant ratio correct, all right, when you're trying to generate these functions. So here's how I would do it. It'd be A times 1 plus R to the x power, okay? And then decay would be f of x equals A times what? 1 minus R to the x power, right? R is the rate of growth or decay. Then in each case, this 1 plus R right here, in each case, that is still your B value, okay? So it's still A times B to the x, but you might have to do a little calculation first to get the correct value for B, okay? That's how you get it. You take your rate, your percentage, either add it to 1 or deduct it from 1, and then that becomes your constant your constant ratio. Are we good with that? That's going to come up on your homework assignment, okay? If it doesn't come up there, it's going to come up on the review for your assessment. I can guarantee you that. We'll work on that when it comes up to time, okay? Now, let's answer problem 16 for a second. Okay, now that you have this information at your disposal, let's answer problem 16. What values of B are needed in order for your function to be a growth function? And then vice versa. What values of B are required in order for your function to be a decay function? Okay, this is a discussion for your groups for about the next 2 minutes. Go. Okay. Think about all different things we discussed and come up with some ranges of values that are going to be acceptable for these 2 different kinds of exponential exercises, okay? Discuss, okay? I want to hear some good conversations that go by. Think about it, okay? Would it be easier if I split it up a little bit? Let the red, the blue groups take growth, and the green and yellow groups take decay. Does that help if you try to do one?
Yeah.
Are we trying to like write down like a definition?
I want you guys to actually, what would be helpful is to write an inequality for me, okay? I would like an inequality that gives me the range of possible values for B, red and blue for a growth function, and green and yellow for a decay function. Okay? So think about it. And I think the new piece of information that I have on the board that we just added might be of some use to you. You guys are yellow, you're doing decay.
Because yellow and green.
Wait, we're working together.
Yellow and green. You guys can work together, that's fine. Yeah, you guys can be big groups and all together, sure.
What do you mean? So, do you just want to write and then look at that?
Yeah. For each case, B has to be in your inequality, okay? Green and yellow are decay, red and blue are growth.
I mean,
So it means
No. Green and yellow are decay, red and blue are growth. Okay?
B has to be less than oh wait.
I just say like E is less than or equal to 1. Sorry. Not less than.
Okay, you guys have some ideas for me? Now, we didn't talk about the restrictions a lot on Wednesday, but I wrote them back up there again. Okay? And when we have an exponential function, these things have to be happening. B has to be greater than 0. Okay? That's a given. All right? That means B can be negative. Right? Okay. Also, B can equal 1. All right? We can talk about that a little bit more on Tuesday, but in essence, if you don't have those things happening, then you don't have an exponential function. Okay? Something else happens instead. All right? So, growth. What are the values for B that would give me a growth function? Who thinks they have the range? Lance?
Anything greater than 1?
Anything greater than 1. 1 plus the rate. That's going to be greater than 1, correct? So that's always going to be greater than 1. So it's going to have to be that's going to be a restriction on that. Okay? Good. Now, back half here. What about the decay range? Merrick? That's exactly right. Okay? Good job. In other words, a fraction. Okay? Everybody okay with those? Both of those? Let's write them down. Okay? So for growth, B has to be greater than 0. Greater than 1, sorry. Okay? And for decay, B has to be between 0 and 1. Does that make sense? Okay. Good. All right. We're in part 3. This is the last part. I think we can get through this part then on Tuesday. Okay? So we're in pretty good shape. And then we'll pick it up on that time. All right? So I'm going to go ahead and stop this a little early today. Just a smidge early. All right. Now, continue to do your assignment as you can, okay? Because I'm probably going to just have you submit one time. So make sure you keep me up with it when you can. Do the problems that you can do. Because you don't have to do the whole thing at once. It's a lot at once, all right? So stay with it some. This might be how some of your assignments are tiered in high school, too. So you need to get some practice with this, all right? Now, before